Hello.
Hi, how's it going?
Pretty good. How you doing?
Pretty good. How you been?
Doing well. Staying busy.
Good.
How about you?
I got a lot on my plate right now, but pretty good. Yeah.
I know that feeling.
Yeah. Uh, so this is actually the first time I'm doing an interview, but it's for my friend Alan at Crypto Answers. I guess you can call me a guest interviewer. Yeah.
Okay.
But it's a pleasure to talk to you. So I deal in graph theory a lot myself, so I'm more familiar with what you're working with than a lot of other people might be. So it was an interest of mine, so I wanted to be a part of this and get a chance to talk to you.
Yeah. So you were doing machine learning and data mining. Is that what you were doing with the graphs?
Yes. A lot of data mining, machine learning. I have an interest in cryptocurrency, but haven't done too much of that in the past. Most of it's been machine learning. Yeah.
Yeah. So machine learning is what I was doing. My PhD was in machine learning a long time ago.
Yeah. I'm not surprised.
Cool. But lately, I've been doing ledgers instead. Mm-hmm. And as for cryptocurrencies, we don't even have one, so I don't have a cryptocurrency to talk about, but I can talk about our ledger.
Yeah.
And that might be of some interest.
Yeah. So, what makes a Hashgraph superior to a blockchain?
Okay. So some people just use the word blockchain to mean all ledgers, in which case we are a blockchain. But a lot of people use the word blockchain to refer to one of the 5 ways you could build a ledger, which is you have a chain of blocks and you do proof of work to put the next one on top. So I could compare to that and to the other 4 as well, or the other 3 as well. If you compare to a proof of work system, one nice thing about Hashgraph is there's no proof of work, obviously. So you don't have to buy a mining rig. You don't have to buy a supercomputer to do it. You don't have to waste lots of electricity to use it. A full node running Hashgraph could be a cell phone. In fact, one of the ways we often test it is with a network of Raspberry Pis. So in a world of low-powered computers and of Internet of Things and of mobile devices, you could just have all of those being full nodes in your network. We don't have to spend a lot of time on the proof of work. Also, we have stronger guarantees. So when you want to know what order are the transactions in, with many of the systems that are based on proof of work, you just become a little bit more sure with each confirmation. But you never know for sure. You just say, well, there have been 6 confirmations. I guess I'm sure enough. Okay, I think I'll get to keep the coin you paid me. I'll give you now a product. But you never really know. But what we have is asynchronous Byzantine. And what that means is you come to a moment where you know for sure you have consensus. Guaranteed, no question about it. It will never change. And there's math proofs that say that it's good. And there's certain assumptions, and I can talk about those. So it's the strongest. Asynchronous Byzantine is the strongest form of proof that you could do. And we have that. Mm-hmm. With a 1/3. It's the strongest thing that math lets you do.
Right.
So that's something nice, is that we have this guaranteed. Not only that, when you know that you have consensus, you also get a cryptographic proof that you could show to a court. So we could say, yes, this has gone through, and you could prove to a court, or you could prove to somebody else. Or maybe a full node is servicing a customer or a client who's just connected over the internet. They can prove to the client, yes, your transaction really did go through and the community as a whole really did agree. That's a good thing.
Yeah.
So we have this strong knowing that you have consensus. We also have speed. We've done experiments where we're going across the country and we're doing tens of thousands of transactions a second, and we get this strong cryptographically proven consensus in a fraction of a second. We've done other experiments where we're going around the world and we get the strong consensus in a few seconds. So it's very fast. The throughput, we've done experiments that are hundreds of thousands of transactions a second. The throughput just basically goes at whatever speed your internet is.
Yeah.
More or less, however many transactions per second that you can actually do the processing on, and you can do the sending out over the internet. If you have a fast enough internet to do a certain number, then we can turn that into a ledger that runs at that speed. So for something like a cryptocurrency or some other systems, the transactions will be very, very fast. Other things would be slower, like if you have a file system and I want to give you a gigabyte file, it's going to take a little bit of time for you to get it. So, it'll be slower. To move money between 2 wallets, you would think would be faster than me handing you a gigabyte file. But whatever speed your internet connection can handle, that's how fast our network can run. That's the throughput we can get on the network.
Yeah.
So we can get a lot of speed, which is really nice. And you don't necessarily get that with proof of work systems. And also for other systems like leader-based systems. Leader-based is nice. There's no proof of work. But the way you put your transactions in order is you send your new transaction to a leader. The leader just arbitrarily decides what order to put them in, and then the leader sends them to everybody. But wait, if there's n of us, then the leader has to send it to n different people. It makes you n times slower. Whereas with what we're doing, it's like gossip protocol. It's as fast as you could do on the internet, and so you'd expect us to be n times faster in throughput.
Yeah.
So we have the speed because it's not based on proof of work. It's not based on a leader. It's certainly not like one of the old voting systems. There's these 30-year-old voting-based systems that have amazingly good math proofs. They're absolutely wonderful, except that they're so slow, to my knowledge, no one's actually implemented one in the real world and used it in a real-life situation.
Right.
And then you have Hashgraph, which has all the math proofs of a voting system, because actually it is a voting system, just one with no votes. So mathematically, it's equivalent to one of those voting systems, but since we have no votes, then we don't have to waste any time sending votes over the internet, and so it's just blazing fast.
Makes sense.
So how are we better? Well, we have the speed, we have the when you have consensus, we have security. So say for a leader-based system, what happens if somebody floods the leader with so many packets they shut down that computer? What if they have a botnet? What if they're doing a DDoS attack, distributed denial of service? Then in one of the leader-based systems, you could just shut down the entire network by shutting down one computer. Now understand, no network can be completely safe from DDoS attacks. If you have enough compromised little computers out on the internet that you could flood every computer in your network and shut it down, then of course you can shut down the network. But you don't want to be so fragile that just shutting down one computer at a time could shut down your whole network. And with Hashgraph, you'd have to shut down a third of our computers to shut down the network. So it's as resilient as you could possibly be. There's math theorems that say you couldn't be more resilient than that.
Right.
So it's not DDoS proof, but it's DDoS resilient. And it's as DDoS resilient as is possible, according to the laws of mathematics and of nature. So that's helpful. Now, of course, people will say, oh, but we have a better leader-based system. Our leaders take turns every 2 seconds. So if you shut down one of our leaders, then 2 seconds later we recover. That doesn't help. The problem is that if the attacker follows the leader and is always shutting down the current leader, they could shut down the whole network for as long as they want by just shutting down one at a time. So the whole goal here is we want to be fast, we want to be resilient, we want to be secure without having to rely on any one node to not be shut down. And we have that because we're asynchronous Byzantine. The asynchronous part means we can handle DDoS attacks. And the Byzantine part means we know we have an answer and it's always right.
Yep.
Okay. And then I said it's a 1/3 thing. You can have Byzantine systems that are more fragile, but the best you can do is we satisfy up to almost 1/3 of us being evil and trying to destroy it. And that's the best you can do. We do achieve that.
Yeah. So,
okay, so
one thing you mentioned was that it's not proof of work, which obviously makes sense. But if that's the case, how are new coins minted and created in the system? If you were doing a cryptocurrency, obviously.
All right. So we're doing permission networks, but we do have demo apps, and one of them is a cryptocurrency. So you could say we have a little cryptocurrency there. Here's the deal. If you have a community that can reach an agreement on the exact ordering of the transactions, and you know when you've reached agreement, then you and everybody independently is processing these to update the state. So you can imagine a state that remembers how much money is in every wallet. And a transaction moves money between two wallets. But if the transaction is supposed to move money from Alice to Bob, but Alice doesn't have any money in her wallet, then the transaction doesn't do anything. So what you do is you have everybody agree on the order of these transactions. Maybe Alice actually tries to send money to 2 different stores, but she only has enough money in her wallet for one of those 2 transactions. What do? We all come to an agreement on the ordering of the transactions. We all know that she gave it to Bob first and then Carol. So we all then, on our own, move the money from Alice to Bob because there was enough money when that transaction happened in the official order. But then the next one in the official order was moving from Alice to Carol. There wasn't enough money at that point, and so we all ignore that one and don't let it move any money. So we're all in agreement to make sure that there's no double spending or no creating money out of thin air because you transfer money from an empty wallet to another wallet and the money actually gets there. we're all enforcing the rules. And the math proof says that if you have a consensus algorithm that's not going to be broken, that you're going to end up with this proof of consensus, and as long as less than a third of us are trying to destroy the system, the bad guys will fail. And so just almost for free, you get, if you've written the rules that we're all enforcing to ensure that, say, the money supply is fixed, then you get the money supply being fixed. No one person or no small group of people can forge money. No small group of people can double spend. No small group of people can convince a store that you've paid it when you really haven't paid it. All of that happens for free if we can put transactions in order and have Byzantine guarantees. Okay. So we don't have a real cryptocurrency. Honestly, for a real cryptocurrency, you need a public ledger. But what we have is a consensus algorithm that works beautifully. We even have a demo that makes a cryptocurrency work on a private ledger. And maybe someday we'll do a public ledger, but right now we're doing the private ones.
Okay, so your technology handles, or would be able to handle, the transactions between people, but really has very little to do with the actual act of creating new coins. That would be something that you would define for whatever cryptocurrency you're building.
That's right. Yeah. And, probably the logical thing is just to say that the money supply is fixed.
Right.
But if you wanted to make a cryptocurrency that wasn't fixed, you could do that too.
Sure. So one thing you mentioned, you don't have a public ledger. Do you have any plans of making a public ledger at the moment?
Yeah, so there's a lot involved in a public ledger beyond just the consensus algorithm. The consensus algorithm is sort of the foundation, and you build your house on top of it. There's lots of different ways you can build the house. Lots of different ways to build a public ledger using Hashgraph. We've been thinking through different ones. We haven't announced any particular one, so stay tuned. Yeah. But at the moment, we have more people who want to be customers that we can talk to just for the permission side. And so we're just working on that. But yeah, maybe someday we'll do a public ledger. I don't know.
Yeah.
Right now we're just focusing on the private ledgers.
Makes sense. Do you have a SDK available for programmers who want to implement and work with the algorithms you're dealing with?
We do. So the way that it works is you go to swirlds.com and you can download our SDK. And what you get is a platform. This is a program that you would run. So we're envisioning a permission ledger. So suppose you and 10 friends want to have a ledger, or you and 9 friends want to have a ledger, so there's 10 of you. You can have whatever number you want. So the 10 of you are going to do a ledger. What you would do is each of you would download the SDK, and you would run this program, that's the ledger, and then you would all run an app on top of that ledger. And the app defines, is this a cryptocurrency? Is this a file system? Is this a game? Is this a stock market? Actually, one of our demo apps is both a stock market and a cryptocurrency all in one app. So it manages wallets and it manages how many shares of each company you own shares in. So what you do is you would write an app that would run on this platform. You and your 9 friends would all run it, and now you have the 10 of you with all the stuff I just talked about. You would probably want to do it by starting with one of our example apps. We have all the source code for them as part of the SDK. And then your app can be pretty simple, because all the hard stuff for consensus is being done by the platform that's underneath it. Your app's just sitting on top of the platform. And so you would just write your app. Probably you would take one of the 6 example programs, start with that source code, and then just keep modifying it until you have an app. And that's what people are currently doing with us. The interesting thing is that we have some additional properties that haven't been in the current systems, like fairness. The leader-based systems don't have this fairness property. And so if you wanted to do such an app, you might include things like a stock market or a game where fairness matters. And we can talk about what that includes, but there's things you might decide to do with this that haven't been done. Or for that matter, you can do a video game where every move is a transaction being put into the ledger. You wouldn't do that on Bitcoin or something where it takes 10 minutes to do a move. But you could, the throughput is so high that you could actually do that. So there's several things that you can start doing now with our SDK that you couldn't do before. In fact, we had a hackathon at Disrupt, at TechCrunch. We had a hackathon, and the winner was an auction site that they built on our platform. But the second place team was a game. And it was fun. You could just play this game in real time on our ledger. And every move in the game is an entry in the ledger, is a transaction going through the ledger.
Oh, that sounds interesting. What's the name of that game? Is it available?
I think it is. It's called Kitten Catch, I think is what the name of it was. And I know there's videos of it out there. If you Google it, you'd probably find the videos. I don't know if they put the source code out.
Yeah.
But what they did is one of our example programs is a game. And so it's, I think they took that and modified it to make it really cute. They have little kitten pictures that are really cute. But actually, in the very near future, we're going to be releasing the next upgrade of the SDK where the game is even faster. I'm going to put some improvements into the example game.
Yeah.
But that's where we are right now. And I don't know, they may have the source code out there. I don't actually know if it's out there right now.
Interesting. So next question. IoT's Tangle. There's a lot of misconception that your technology is similar or the same as IoT's Tangle. And obviously it isn't, but I'd like to hear in your words how it differs and why your system may be better or maybe just entirely different from IoT's Tangle.
Oh, yeah. Well, it's entirely different. It's trying to achieve a different goal, and it's doing it a different way, and the properties are different, and the math is different, and pretty much everything you can imagine about it is different, except for the fact that they both have a graph in them somewhere. So they have a graph in them. That's what they have in common. But other than that, it's completely different. So in the Tangle, a graph in graph theory is circles with lines connecting them. In the Tangle, a circle has a transaction in it, and its ancestor is in the graph. It's a directed acyclic graph. The ancestors are a set of transactions, and every time you add a new one of these circles, you pick two of the existing ones that are at the tip, and the choice of which ones you pick is in some sense you are saying, I really like the set that's represented by this tip and this tip more than the set represented by some other tip. And so in some ways, if there's two conflicting transactions like a double spin, you're voting or you're giving your opinion on which of the two should be part of the system, and there's an algorithm for how you do that. So these circles represent really a set of transactions, and the lines between them are almost like votes or adding weight to one set over another set. Make sense?
Yeah.
Okay. For us, it's entirely different. We have circles and lines, and the circles contain the transactions, but they represent a radically different thing. So in Hashgraph, we're all just talking to each other randomly. It's just gossip. So if I have a new transaction, I'll tell a random person. I'll call you up randomly and tell you, and then we'll each call someone else randomly and tell them, and 4 of us will know. And then we'll each tell someone else randomly. There'll be 8 of us. And it just explodes outwards, faster than wildfire, exponentially fast, until everybody knows this transaction. And it's just because we're all calling each other randomly. Our graph, the thing that we're gossiping about, represents the history of exactly how we talked to each other. You can look at this graph and you can say, oh, I see. The last person I talked to was Alice, and before that, she talked to Bob, and after I talked to Alice, I talked to Carol. You get the complete history of how we have talked to each other. So when I create one of these circles, it's not representing a vote on which set I like best. It is representing the event of you having called me and told me everything you know. It's actually representing that event of us gossiping with each other. It's like a record of our history. And it contains inside of itself the hashes of 2 other nodes, so it's lines going to 2 other circles. But those lines represent the last one of these circles that I created and the last one that you created. So it's representing the fact that you called me and told me everything you knew, and it's giving us an idea of where in my personal history and where in your personal history that event occurred. So the graph is actually a complete history of how we've gossiped to each other. It's a picture of our gossip history. And we are gossiping these circles. When I call you and tell you everything I know, what I'm doing is I'm telling you whatever circles in the graph you don't know about yet. So I'm gossiping about this graph. But the graph itself is the history of our gossip. And so I'm gossiping about gossip. It's weirdly self-referential. We're not just gossiping about transactions, we're gossiping about sets, we're gossiping about which sets we like. We're gossiping about gossip itself. That's weird. But what it does, by giving us this history of how we all talk to each other, it means that I don't just know all the transactions. I know what you know, and I know when you learned it. And I know what you know about what Alice knows. And I know what you know about what Alice knows about what Bob knows. And I know when he learned it. I know so much about the information available to each person in our group that I could actually run one of those 30-year-old algorithms that are so incredibly wonderful mathematically and totally impractical. I could say, you know what? If we were to run one of those old algorithms where we're sending billions of votes over the internet, I know so much about what you know, and when you knew it, I know how you would vote. So, let's run the algorithm, but don't bother voting. Just, I'll pretend you sent me the vote, because I know exactly how you would have voted, so I'll just pretend you sent me the vote, and we'll be happy. And everybody will see everything you've always known, and everybody will know how you would have voted. And so you don't have to send your vote to anybody. We just all know. And so you get this magical property that we gossip about gossip. That means I have to send you the transactions in these events, and I have to send you a few hashes. Every time I send you a collection of transactions, I also have to send you 2 pointers. That's all. So I have to send you the transactions. I've added a tiny bit of extra information, maybe 1% more bytes that I have to send you. And then magically, once you get a transaction, a little bit later, after you've received a few more transactions, you know the consensus on what order this transaction was in. You don't have to send any votes. You don't have to receive any votes. You don't have to talk to anybody. There's no leader involved. Everybody is equal. You just know the answer because you run the whole election purely in your head. It's virtual voting, and you just know the answer. And you have all these strong math proofs that it's right. It's asynchronous Byzantine for the same reasons that all these voting algorithms for 30 years have been asynchronous Byzantine. But we do it with no voting. And that's it. That's the Hashgraph algorithm.
So it sounds to me that a lot of this, what it comes down to is you've solved a lot of the scalability problems that a lot of blockchains have. There's less crosstalk needed. You know things without needing to talk to a specific node to find that out. Now, one of the problems I don't think we've spoken about is the problem with a lot of these blockchains having a record in their blockchain that has every transaction going back to the beginning of time and every transaction that ever will happen, which means they grow and grow and grow, and they wind up being hundreds of gigabytes and, long into the future, terabytes and who knows what else. So the question is, does your algorithm in any way address that and reduce the size on a blockchain and prevent the need to go back to the beginning of time?
Excellent question. Shorter answer is yes, we do. The longer answer is, but only if you want to. So here it is. What we do is we come to a consensus on the order of the transactions. But when you hear about a new transaction, within a fraction of a second or maybe a couple of seconds, you will know its consensus order. At that point, if you really wanted to, you could write it to your hard drive and keep a record of every transaction in all of history in consensus order. You could do that if you wanted to. And in fact, you're actually going to get digital signatures from other people that you could prove to a court that it's true. So if you want an audit trail, have at it. Terabytes are cheap. Buy a terabyte hard drive and you can keep your audit trail. But what if you don't want to? What if we're playing, say, a video game? You don't want to record every move in the entire history of the video game for eternity. There's no point in that. You just want to store the state. I want to know where each player is and how many lives he has left and how much ammunition is in his gun and what possessions he has. A tiny bit of information. And that's all that you have to store. So you receive a new transaction and it says, Leemon has just walked 1 meter north. All you do is you process that, well, you hold on to it for a fraction of a second until we know the consensus. Once we know the consensus order, then you just go through the transactions in consensus order, and when you get to that one, you take the spot in memory that remembers where Leemon's location is, and you change it to be 1 meter to the north, and then you can just throw away that transaction, and you never store it again. And all you're having to store about Leemon's character is his location. That's it. You don't have to store the history. And so the amount of state that you store can be incredibly tiny. You could have, you talk about cryptocurrency. You could have a cryptocurrency with, say, 1 billion wallets, and it would just be a few gigabytes to store the current balance of all the wallets. Or you could do a hybrid system. And by the way, if you only have 1 million wallets, then you only have a few megabytes you have to store. You could also do a hybrid system. You could say most of my full nodes are just going to store the current state, megabytes or gigabytes, which is almost nothing. My phone has 256 gigabytes. So that's a lot of wallets, right? So you could just have a few of your nodes are just storing the state, it's nothing. And a few of your full nodes store an audit trail going back to all the beginning of all of history because they have a giant hard drive. you don't have to do both. And when some new node wants to become part of the network, all you have to do is give them a little tiny current state and prove to them mathematically that it is correct. You don't have to give them the whole history going back to a Genesis block. But when the auditors come to your door, you can hand them your terabyte hard drive with the history all the way back to the Genesis block. So that's a third option, is do a hybrid. Let some of your nodes, some of your full nodes, store all the history because you like to have all the history. Have some of your nodes store just the state, and then a cell phone or a Raspberry Pi could be a full node. You can do whatever you want. And I got to talk about graph theory. I said you could store all the transactions in all of history. You can do that, and you can even use digital signatures and chained hashes to prove to an auditor that it's correct. But you know what? If you wanted to store just 1% more information, you could store the entire hash graph going back through all of history. That would tell an auditor that these are all our transactions, that this is the order, and it would prove to them that the community agreed, and it would be physically impossible for you to delete a transaction without the auditor noticing it, as long as you're using strong digital signatures and strong hashes. So you'd have all that. But in addition, you would have a graph showing how everyone talked to everyone else throughout all of history back to the very beginning. And you could do data mining to say things like, what was the internet weather like, and how does it change over time? And you could see some nodes are faster than others, and you could see patterns of how they're operating. Maybe you could see ways to tune our software to be faster. You could do incredible amounts of data mining if you're the kind of person that likes doing data mining on large graphs, hypothetically speaking.
Right.
If you like that sort of thing, you would have an amazing database. And if you want to, you can make all your full nodes throw away all that information, except maybe have one or two of the full nodes store all that information. And then you do your data mining on those two nodes. I'm really excited about this. And in fact, even our current software has these screens that show you amazing amounts of information about how the network is running, just because we can.
Yeah, one of the things I like about this is we have a lot of cryptocurrencies out there, for example, Ethereum being one of the leading cryptocurrencies, and they're struggling with this problem of, the data set is getting too large for them. And one of the problems is the security of their network is dependent on how many full nodes you have. And it sounds like in your case, you can have the security of the network is not dependent on the number of full nodes. Those truncated nodes can provide just as much security to that network. And all you really need is one copy of the full history somewhere if you need that. So you don't need a million copies, just, cloud storage somewhere, one copy for everyone to share, and that's good enough for those auditors when they come along.
You're right. And to be clear, when I was saying full nodes, I was even including the truncated nodes. I just meant a full node is a full-fledged member that helps the community work. But what you just said is exactly right. You could have everybody be one of these truncated nodes that uses almost no memory. For some applications, like a file storage system, they would need a lot of memory.
Yeah.
But for a lot of applications, like a cryptocurrency, it's almost no memory. And then maybe you just have one node storing it, and you have a guarantee that they cannot maliciously change what they're storing. If you ever ask them to give it to you, they can prove that it's real. You might worry they might delete it, though. So maybe you'll have several nodes store it just because we don't trust anybody.
Right.
Right. But yes, you could do exactly that. And the security is entirely how many of these nodes you have, not how many with the full history you have. It's just how many do you have, period, including the truncated ones. So yeah, that's true.
Wonderful. So one last question for you. I was reading and I noticed that this technology is actually patented. Do you think that's going to hinder adoption from, obviously, the open source community, other cryptocurrencies that may want to implement this? And even if you were to implement a cryptocurrency at one point, would people want to use coinage from a cryptocurrency that, someone owns a patent on and can, charge whatever they want in royalties for people to use that? And, how are you dealing with that concern?
Yeah, so sure, good question. So right now we're doing permission networks, and our customers really don't mind it being patented. In fact, some of our customers in the financial industry actually like the fact that we do it this way. So it just hasn't been an issue. It's literally a non-issue. We are also talking to possibilities of, for example, you have some of the big stacks like Hyperledger that are pluggable, and there's a consensus module at the bottom. And we would just say, hey, anybody who wants to set up a permissioned ledger can use this for free. But if you would like greater throughput and greater security and fairness, then you can just buy the premium module from us and plug it in at the bottom of the stack. So, we're talking about doing things like that in the future. So again, it's not a problem. People are used to that sort of thing. It's like databases. You can get open source databases right now, and a lot of people use those, but then some people pay for the premium model that isn't open source. So, both coexist. There's room for both. And for public ledgers, we haven't even done anything with that yet, but, we'll worry about that when we get to it.
Yeah, it sounds like that's not really one of your concerns or a target right now. So, and that's really where the problem of patenting would really come in, just a public currency. I don't know how the public might respond to that. And with the stuff you're doing, I don't see it being a problem. So that makes a lot of sense.
Yeah. So we'll worry about that later.
Yeah. Well, it was nice chatting with you. Is there anything else you'd like to mention before we bring this interview to an end?
No, it's been great talking with you, and be happy to talk with you any other time.
Yeah, it was a pleasure. And
Swirlds.com has the SDK if anybody wants to play with it. It also has the papers with all the math proofs. If you're into math, we have very formal math proofs that show all this stuff that's really cool. And we also have a bunch of videos where I explain it without so much math. So all that stuff's there if anybody's interested.
Yeah, it's some wonderful explanations. I took a look at it. I'm a math expert myself as well as a programmer, so I guess I have a bit of an advantage, but I do think it was written in a way that a lot of people would be able to get a lot of the important parts from it. So I think it's a wonderful collection of documentation you have.
Cool.
Yeah.
Well, glad to hear it.
Yeah, so I hope everyone checks it out. It was nice talking to you, and hopefully we'll get to chat again sometime.
Yeah, I hope so. Thanks.
All right.